Hi everyone. In this video we're going to talk about the alveolar gas equation, which is a sort of fundamental equation in respiratory physiology and one that's not particularly well explained in my opinion online at other sites. So the alveolar gas equation relates the partial pressure of oxygen in the alveolus, specifically the steady state partial pressure after gas exchange in the alveolus. We're trying to relate that to the pressure in the atmosphere, the fraction of inspired oxygen in the atmosphere, and the partial pressure of CO2 in the arterial on the arterial side. And basically we're trying to estimate our partial pressure of oxygen in the alveolus using measurable, observable quantities that are available to us in a clinical situation. And so we're going to get to all these quantities in greater depth, but this is the fraction of inspired air that is oxygen. This is our atmospheric pressure, PATM. That's pretty self-explanatory. We're going to get to PH2O in a second, and we'll get to the respiratory quotient, but this PaCO2 is the partial pressure of CO2 in arterial blood gas. And we'll get to all these things in greater detail. Okay. So the first thing that we want to do is we want to calculate, so remember PaO2 is the pressure in the alveolus. We want to calculate the pressure of oxygen, the partial pressure of oxygen right outside the alveolus. So remembering the anatomy of the alveolus, basically what happens is we have inspired air, which is nice room air out here. It comes into our airways, and then it travels into the alveolus where gas exchange occurs, right? The alveolus is the end part of the respiratory system, of the respiratory tract. And right before we get to the alveolus, there is going to be a partial pressure that is not influenced by gas exchange, right? Gas exchange has not yet occurred, so I'm going to call that PbO2, or sort of bronchiolar oxygen concentration, or oxygen partial pressure. A quick side note, just to sort of elucidate some of the aspects of partial pressure. Remember that pressure is related to density or to concentration by the ideal gas law. So PV is equal to nRT. We can realize that partial pressure, or P, the pressure, is going to be related to N over V times RT. And N over V, the number of moles over the volume, this is a measure of concentration. So in other words, partial pressure, even though we use the term pressure, we could easily substitute the word concentration and we get the same exact results. It's just by convention that we use partial pressure instead of concentration, and partial pressure is a little bit easier to measure because we measure a pressure and then we measure a fraction and we can get partial pressure as opposed to just measuring the concentration. But ultimately, I think from a chemical or chemistry standpoint, the concentration is really what we're talking about. So I just wanted to touch on that for a second. Okay, so we have our PbO2, the partial pressure or concentration of oxygen in our bronchioles right before we get to the alveolus. And this is going to be related to the fraction of inspired oxygen. So the number of these, the inspired air, the fraction of inspired air that is oxygen, and that's around 20% usually. And it's going to also be related to the pressure, the atmospheric pressure, or the atmospheric density, you could say, right? Because remember, concentration or density, N over V, is related to pressure. So it's going to be, the concentration of oxygen in our alveolus is naturally going to be related to, well, what fraction of the inspired air is oxygen, and how dense is that inspired air? What is the concentration of the air itself? So these two parameters are going to be important. The other thing that's going to be important is that, well, inside of our airways we have a lot of water. And what that means is whenever water is present, specifically at a high temperature, like the 37 degrees that we have inside of our body, what happens is that some of this water will evaporate. And specifically there is a fixed amount of, it will evaporate. There is some equilibrium between water and water vapor, and that equilibrium will produce basically a fixed amount, a fixed partial pressure of PH2O. In other words, there's some fixed concentration of water that basically describes the equilibrium between the water phase and the water vapor phase. And we have to take that out of our atmospheric pressure because basically water occupies some of that, that atmospheric pressure. And remember, the pressure, whenever we have a static situation, right, the pressure throughout the whole tube has to be atmospheric pressure. Otherwise, we would have gas flowing. So if we have a static situation, you just took a deep breath in and you're holding it there, there's a equilibration of the pressures, that happens because, otherwise you'd have gas flowing. So, basically we have to take out of our atmospheric pressure a certain amount of concentration of water, and the remaining, out of that, there's some fraction of the remaining stuff that is oxygen. Okay, so this is our expression for bronchiolar partial pressure of oxygen before any gas exchange has occurred. So now let's talk about gas exchange. Okay, so some assumptions that we're going to make now are that basically the gas exchange phenomenon here is going to be explained by this concept of V dot O2. And V dot O2 is going to be equal to, is going to be defined as the consumption of oxygen, consumption rate of oxygen. And we're going to assume that the consumption rate of oxygen here, we're in some sort of steady state, right? So that the amount of oxygen that is coming into the system is equal to the amount of oxygen that is being consumed by the system. So there's no, we're at a steady state concentration here of oxygen. And so what that means is that if we think about it, well, if we have some sort of consumption rate of oxygen, the amount of oxygen that is consumed has to be equal to, well, if we have some sort of PbO2, let's try to relate this to the PbO2 and the PaO2, right? Which, remember, we're trying to say how much oxygen is being lost due to gas exchange, right? How much oxygen is being lost due to gas exchange? Obviously, that's going to be related to our V dot O2. So how do we relate these quantities? Well, the V dot O2 is going to be related to our concentration of inhaled oxygen minus our concentration, or the concentration of oxygen in the alveolus, right? So the difference between these two is going to be a kind of measure of how much is being consumed. But also, it's not just a matter of the concentration. And sorry, I should mention we have to actually tack on a constant here, 1 over k, because we're not, to go between concentrations and partial pressures, we just have this 1 over k constant, which kind of allows us to do that, but that's not super important. So we have this concentration difference between the inspired oxygen and the oxygen in our alveolus. And so V dot O2, which is the consumption rate, now we just need to multiply this times our alveolar ventilation rate. So this is saying what is the difference between the concentrations coming in and out, so delta concentration, and this is saying how much volume is coming in and out, right? So basically that multiplying those two terms will give us how much, what is the total number of oxygens that are going in that are being consumed basically by this system. Okay, so we have now our expression for V dot O2. Now, if we knew what the V dot O2 was and what our V dot A was, then we could solve for PaO2, right? We know our PbO2 right up here. If we knew that those quantities, if those quantities were measurable, then we could figure that out. But the issue is that those quantities are not particularly measurable, right? It's not easy to measure your V dot O2 and your V dot A necessarily. These ventilation rates are not that easy to measure. So what do? Well, instead we turn to a gas for which the equilibrium dynamics are a lot more simple, and that gas is carbon dioxide. Okay, so let's look at carbon dioxide. So right now we're gonna basically relate. So if we have our carbon dioxide production rate, right, that's the other that's the other gas that is primarily participating in gas exchange. So V dot CO2 is a lot simpler because we know that our carbon dioxide is extremely well diffusing across the alveolus. Basically, whatever carbon dioxide concentration that we see in our arterial blood gas, if we see some PaCO2 in here, that is basically going to get fully equilibrated with the alveolus very quickly because carbon dioxide diffuses very, very quickly. And so if we look at now, so remember, if we have our concentration of, so I'm writing partial pressure of CO2, but partial pressure of CO2, remember, in the alveolus is the same as the partial pressure in the in the arteries. And so this quantity here represents the concentration of CO2, basically in our alveolus. I tacked on that 1 over K. And if we multiply that times our ventilation rate, now we get the amount of production of CO2. Or, sorry, actually technically we get the excretion rate. And, at steady state, this is going to be equal to our production rate. So if we assume steady state for CO2, that there's not any more CO2 being produced than excreted, in other words, our CO2 arterial concentrations are stable, then our production rate and our excretion rate are going to be equal. Okay, so now we have this concept, we have some an expression for our production rate of CO2, and we have an equation that basically relates our consumption rate of oxygen to our concentration difference across the from the bronchioles to the alveolus. Now the question is, how do we relate V dot CO2? How do we relate our production rate of carbon dioxide to our consumption rate of oxygen? And it turns out that this is the job of the respiratory quotient. So respiratory quotient basically relates V dot CO2 and V dot O2, because basically what it tells us is, this ratio is nothing more than a stoichiometric principle that is related to the metabolic composition of our diet, basically. So, if we have more more carbohydrates or more lipids, that ratio of carbon dioxide to oxygen, carbon dioxide produced to oxygen consumed, will change based upon the fuel that we're using. And so this respiratory quotient is basically a measure of what fuel we're using, and for most diets it's around 0.8, for a standard sort of mix. Okay, so we get this respiratory quotient, which relates, again, our produced CO2 to our consumed O2. And now we can given that we have this relationship, now we can use the fact that we have this nice measurable quantity right here, this PaCO2, which, unlike our oxygen sort of measuring quantities, is much more easy to measure. And so what we can do is we can basically say that V dot CO2 divided by V dot O2, which up there, which is our respiratory quotient, and that's going to be equal to, if we divide those two expressions at the top, we get basically, our VA's cancel, our 1 over K's cancel, and we get PaCO2 divided by PbO2 minus PaO2. And so if we rearrange this around, we get PaO2 is equal to PbO2 minus PaCO2 divided by respiratory quotient. And if we remember up top that PbO2 is equal to F times PATM minus PH2O minus PaCO2 over RQ, and this is our answer. So I think the part that's worth pointing out is that this PaCO2 over respiratory quotient is kind of a strange quantity. It's not really related to our alveolar oxygen directly. It's instead a stand-in for this V dot A, basically. So you'll notice that if we hyperventilate, right? If we ventilate so that we're pulling in more oxygen at every breath, theoretically, if we hyperventilate, our PaO2 should be increased, right? Because now we have, every time we take a breath, our PaO2, meaning our alveolar oxygen concentration, because now the amount that is being lost to gas exchange is going to be lower, right? If we're hyperventilating, because we're taking a breath more frequently, there's not as much lost every time we take a breath. But the issue is we can see that's not really reflected in our equation, right? Where is our ventilation rate? Where is where's hyperventilation come into this? So PaCO2 is basically a stand-in for our ventilation rate, and it relates Well, okay, we know that our ventilation rate is going to be related to our PaCO2, right? Inversely related to that, right? If assuming that our carbon dioxide production stays constant, so assuming that V dot CO2 stays constant, then as our ventilation rate increases, or as our alveolar ventilation rate goes up, our PaCO2 will go down, and that going down of this is what's going to be reflected in our arterial, in our alveolar oxygen concentrations going up. And so the way that I would think about it is that this PaCO2 term is kind of a stand-in. It's giving us a sense of the respiratory exchange, the gas exchange that is going on, without having to measure any quantities relating to oxygen directly, because PaCO2 is such an easy thing to measure, and the alveolar and then the sort of gas exchange equation for CO2 is so much simpler. And so that's kind of how I would understand the alveolar gas equation.